So let's continue this concept now a little bit to grow into the global circulation things. So we are going global. Global thermostatic effect. Thermostatic basically means, you know, the thermostat you set for the refrigerator and the air conditioning and so on, which is a way to control the temperature to resist the change. That's thermostatic effect. So water's properties moderate temperature on Earth's surface. So water heats slowly and cools slowly because its specific heat capacity is very high, right? So the Earth is a sphere. Sun's energy coming from far are parallel to this sphere, which means if you imagine a basketball and you are using a flashlight or a torch at it, then the light is going to be more on the center of the ball. As you go towards the edges, the light is going to be less, right, because of the curvature. So Earth is receiving a lot of energy in the tropics per unit area from the sun. The same parallel rays are actually going to be putting in less energy per unit area at higher latitudes because of the curvature of the Earth. So if you keep on putting energy, then how warm the temperature gets depends on how much energy is being lost. And the sun is putting energy, something else is going to send the energy back to space or back into the atmosphere. We'll see later on. So the equatorial oceans are constantly receiving energy from the sun, but they do not boil. Polar oceans are constantly losing energy, as we will see, because they receive very little of the sun's energy. But because the snow and ice are very reflective, it loses whatever energy it is receiving. And then there is other energy called infrared energy that everybody is also losing, because any warm body, right? Warm doesn't mean certain temperature. Warm means greater than 0 degrees centigrade or even at 0 degrees centigrade. The body, for example, if you go near it, you can feel the heat. That's infrared energy. Some of the animals that wander around at night can see infrared images, whereas we cannot. So the soldiers wear infrared goggles to see things in the dark and so on. So the net energy balance of incoming solar energy and outgoing infrared energy determines how much net energy any region is receiving. We'll see later on that the tropics are receiving more energy from the sun than they are losing to space by infrared, but yet the equatorial oceans do not boil, and the polar oceans, even though they are net deficit energy, they do not freeze solid. There is Arctic Ocean, there is the Southern Ocean. Antarctica is a continent which freezes, but Southern Ocean is still liquid state. So why does this happen? Basically, we are moving energy, right? Heat energy is exchanged in evaporative and condensation cycles. So ocean is evaporating heat, it's condensing in the atmosphere, so energy is being picked up by the ocean and released into the atmosphere. So essentially we'll see again and again that the excess energy from the tropics is constantly being moved to higher latitudes where there is a deficit of energy. That's what gives us weather and climate. That's what gives us winds in the atmosphere, clouds and rain. These winds then begin to drag the ocean around, so the ocean currents are created, and there are regions where the ocean cools enough that the water gets heavy and it sinks, so ocean is moving horizontally by the winds as well as vertically because of the density changes. And that's what being shown here, atmospheric heat transport. So it's showing evaporation latitudes, which you can see is away from the deep tropical oceans around the equator. And there are regions where evaporation is more than precipitation, which means there are more water being lost from the ocean than is falling back as rain. And there are latitudes where more precipitation is falling than is being lost as evaporation. Why are the tropics not evaporative despite having so much sunlight? It's because there is constantly condensation and rainfall happening as well in the tropics. So tropics are warm, they're evaporating a lot, but the rising air, warm air that rises, expands, as we will see later on, and the water vapor that's in the air condenses and it rains. So a lot of the evaporated water is falling back as condensation, condensed precipitation. There are reasons why these latitudes are evaporation latitudes. When we look at the atmospheric circulation, we will see why this region receives less rain than the evaporation it's experiencing. That water vapor is moving north and is precipitating over there. So essentially you are moving energy from the ocean into the atmosphere, and the atmosphere is moving energy north towards the poles to make up for this excess energy in the tropics and deficit energy at high latitudes. So these are the global thermostatic effects. The marine effects is that because you have high heat capacity of the water, it's warming slowly and cooling slowly, and the continent on the other hand has a very low heat capacity, so it's warming up quickly during the day and cooling down rapidly at night. So if you look at the day-night temperature difference over the globe, you will see that the ocean has very little difference between day and night. Surprisingly, there are some places which are actually warmer at night than during the day, which we will not discuss right now. There are reasons why that happens, has to do with clouds and how clouds can trap the outgoing long wave energy at night and make the nights warmer, whereas during the day you have the clouds blocking the sunlight that is coming to the surface. So deep into the interior of land, you will see that the difference is higher. This is being shown for a particular month of a particular year, but it doesn't matter. You can look at many months, many years. The picture remains almost the same. January is summer in the southern hemisphere and winter in the northern hemisphere. That makes some difference, but nonetheless, you can see that places like the Sahara, the daytime temperature is much higher than the nighttime temperature, and interior of the land is larger day-night difference than near the coast. Why? Because near the coast the ocean is warming slowly during the day and cooling slowly at night, so it can send winds from the ocean to land and land to the ocean depending on who's cooler, where the pressure is higher. So you have what is called the sea breeze. This moderates the temperatures near the coasts. So typically islands, even though Tasmania is very far south, for example south of Australia, because it is surrounded by the ocean, it has what is called maritime weather, because the temperature swings are much milder, whereas if you go on land like the Sahara or interior places in the US and Australia and South America and so on, the daytime temperature swings can be much larger because you're away from the moderating effect of the oceans. So everything matters, right? So heat capacity of the ocean, of the land, how the winds move, how the daytime energy balance happens, how the nighttime energy balance happens. All these together determine the diurnal cycle, the temperature range during the day from morning to evening and